So we're looking at function intro and our function notation kind of lesson. The intro was something that I asked you to look at when you were at home after we took our test. So this was an at-home video, the function intro. Function notation is what we're going to be covering in class. So we either covered it Thursday or covering it on Monday, depending on your cohorts. I'm going to kind of go over some of the important pieces from our function intro. So our unit on functions begins with a relation. Relation is a connection between input values and output values. So what we're trying to do is we have something coming in, and then something comes out for that input. The study of functions relates us to when every input has exactly one output. So it sounds like in this function that the outputs are the important part because it's exactly one, but it's really the inputs. So domain is our list of all input values, and the range is the list of all output values. Rate and change and slope, something that we didn't talk in that video. Hopefully we're a little bit familiar with them. Rate and change, so this is the change in y over the change in x. It's also known as rise over run when we're talking about a graph. Y-intercept is the point where the line crosses the y-axis. So if I were to draw a picture for the y-intercept, and we'll do one for rate of change, why not? We're drawing a picture here. So here's our line. The y-intercept is this point right here. And then the rate of change or slope is the steepness of the line. So let's even add that too. The steepness of this line, and that's where we get all these other terms that help, like, they're probably kind of confusing because there's a lot going on. So the steepness of this line is measured by finding how far do I go from this point to like this point, how far up and over. Maybe to the up and over, up and over. That's our steepness. That's our slope right there. That's kind of what dictates it. It kind of looks like a set of stairs. So if I were to draw some pictures to give you another idea, really steep stairs. So if you think about really steep stairs, what makes stairs super steep is they're incredibly tall, but where you put your foot is like really narrow. So because it's really steep like this, gives you a steep set of stairs. Most stairs in houses are pretty equal. The same distance up is the same distance over. Same distance up, same distance over. Same distance up, same distance over. Gives you a pretty non-steep set of stairs, but it lets you go up, actually up them. Some of the really, really, really non-steep stairs, I find them outside of buildings all the time, where you like take one step up and then it's, you have to run a mile basically to get to the next stair. It's way over here. And then it's way over here. As you can see how steep these kind of lines are. They're like not steep at all. So that's all the rise compared to the run. And then a graph rise is with y, run is with x. So that's how we get the y over x bit. All right, so determining functions. How do we know if something is a function or not? So we're going to look at just tables for right now. We're going to introduce the other ones as we go. Determining functions. What we really are looking for are the input values. So we look right here. What we're looking for is we're looking for repeats right here. For about 99% of this, we don't even care what these numbers are. Basically, I could do this, and you'll have a decent idea if something's a function or not. Let's say 90% of the time, you look right here and you're going to know. They're all different. Doesn't matter what's on this side of the shade. This is a function. So if we look at another one, okay, again, I'm going to cover up this side because this side, those numbers don't even matter right now. We see a 3, we have a -5, a 2, and another 3. All right, immediately, we're looking right here at these 3s. We're pretty suspicious of these 3s right here. We're like, what seems to be going on with them 3s? So that's when we're going to have to turn our attention to the other side. Because these 3s, we're going to try to see what they're paired up with. All right, I know I haven't written the numbers yet, but we're just setting the stage. All right, this one's a 1, this is a 5, this is a 100, and this is a 1. Because these two pairs are exactly the same, we have ourselves a function. All of the numbers, see, it's like this. If we take out, so this 3, because it's 3 and 1, we basically don't need it. It's extra info. I accidentally erased the 2, so I'm going to try that again. This is extra info. We don't need it. We already know that 3 goes with 1. So by taking that out, do any of these numbers on the left repeat? The answer is no. Function. One last one. Yes, you guys can guess it. It is going to be not a function, but we're going to, again, look at that line. I know, pretty good at drawing straight lines there. All right, so we've got -2, -1, 0, and back to -2. All right, again, right here we're suspicious. What's going on? With this 2, we see 4, we see 100, we see pi, because it could be a number, I don't care. We don't care about the outputs, we only care about this one, and it's a -10. Because we can't make a distinction between what number should go with the -2, I can't just erase it. I don't know. Question marks. This one is not a function. All right. The next thing that we're looking at is function notation. So function notation looks like this. F of x is equal to, and on this side is some rule. Now the rule I'm going to put for this example we're going to write about is 3x plus 5. I just made it up. Doesn't really matter. So 3x plus 5. So with our function notation, this x right here is input, and so is this x right here. It represents our input values. So we're going to plug numbers in. We're going to see what we get out. The hard part about our function notation, or I guess not the hard part, the weird part, this x right here doesn't actually exist in the equation. So anything that this x is, if it's an x, it's a number, you can't do anything with it. Do not try to multiply. Don't divide. Don't subtract. Don't anything. That number, this whole side, this f of x, this whole thing, you basically just rewrite it every time. It doesn't go anywhere. It doesn't interact with this at all. It's all this right-hand side rule. The f of x, the whole thing, I'm going to have us write it again. So the f of x here, this term, represents the output. And like we mentioned over here, this 3x plus 5 is a rule. So how it works, we're going to have a t-chart over here to record our x's and f of x values. F of x is really just a fancy y. I'm going to plug in, let's say 5, into my function. 2x minus 1. So x is going to become 5. So I got f of 5 is equal to 2. This x becomes 5. Super important, we put it in parentheses. Minus 1. Again, this 5 doesn't exist. So we don't need to do anything to bring it over here. All we have to do is evaluate this right side. 2 times 5 is 10. 10 minus 1. So when I plug in 5 into this function, it spits out 9. And I record that in my table. If I plug in another number, say, negative 3, f of negative 3, we get 2 times negative 3 minus 1. F of negative 3, again, I'm just going to rewrite this literally every time. Nothing else happens with it. 2 times negative 3 is negative 6. Negative 6 and negative 1 gives us negative 7. I record it. That's how function notation works. I'm going to do one more, but I want to do a little bit different function. So again, I'm going to get a t-chart here. My function in this one's going to be x squared minus 3x. All right, and I'm going to plug in negative 4 for my x value. All right, so now it's f of negative 4 is equal to negative 4 squared minus 3 negative 4. Negative 4 squared is negative 4 times negative 4, positive 16. Negative 3, negative 4 gives us positive 12. Add those together, and f of negative 4 is 28. We record that in our table, and that's how we use function notation.